I'll just open it up. This is the, can you see the, now about the overview, I'll just give you the overview on linear operators. This part of the material I have taken from the book of Limaye. I will bring a soft copy of that when I come to Mizoram. I'll be there on Sunday, this Sunday. This is the linear maps, okay? Now, let X and Y be linear spaces over real or complex, which is denoted as K. F is called linear. F of K1 X1 plus K2 X2 is F1 of F of X1 plus K2 of F of X2. That's the linear map, okay? That's the definition. So, for X1, X2 in X, and for two scalars K1, K2, there are two important subspaces we associate. One is called the range space, which is normally denoted as R of F. What is this R of F? It is set of all Y. Y is in the range, okay? Range of the map. Y is in Y such that there is some X in the domain space such that F of X equal to Y. This you know, range of a function. It's called the range space. It turns out this, see, in general, range may not be a linear space, but if F is linear, then range space is linear. Z of F is set of all X in X such that Fx is 0. That means this X becomes 0. That is why you have this, this notation Z. Z means 0 space of F. Okay. Some people use N instead of Z. Okay. Let X and Y be two non-linear spaces over K. Let F be a map, linear map X to Y. Then F is injective. F injective means F is 1, 1. It's a 1, 1 map. If and only if the null space is the 0 space. And in that case, the inverse function from range of F is also linear. Okay. You have to be careful here. Huh? We are not saying the function is invertible. Okay. The range of F need not be Y, but on the range, the inverse will be linear. That means if the function is linear, then so this is the second, you have done this theorem or not? Theorem 2.4. Very important. Huh?
Rank nullity theorem, sir.
Huh?
Rank nullity theorem.
This is not rank nullity. Yeah? This is a map. F is 1, 1 if and only if the null space is 0. Have you done that or not? It's simple. And second thing is the inverse of the function on the range is also linear.
Proof of this theorem, sir. We don't.
Will you read it yourself? Or should I do it? You said overview, no? I am doing it on a vector space, not on non-linear space. Rishabh said you do a review. That's what I'm reviewing here. Okay.
We can read, sir.
Okay. All right. The proof is here. Proof is simple.
No yes, sir. Yes, sir. Yes, sir.
Now we come to the continuity of linear maps. How do you define the continuity of a linear map? If you have two non-linear spaces, then F is called continuous if it maps convergent sequences to convergent sequences. That's the definition, usual definition. Otherwise, F inverse of the open set is open set. That becomes a little complicated. Let's work with sequences. It's easier. This X and Y being non-linear spaces, it is also metric space. So it is saying that definition is the same as what the definition of continuity in a metric space. Okay. That is the first comment made in the book. Okay. For the second, the theorem, if let X and Y be norm spaces, non-linear spaces. Please note, we are not saying whether it is finite dimensional or not. If F is finite dimensional, then every linear map is continuous. So obviously, the question now is, if X is not finite dimensional, that is infinite dimensional, and Y is not zero, that is Y is a non-zero linear space, then there is a discontinuous linear map. That means every linear map need not be continuous. So this is the first theorem that we are doing. It's a simple theorem. Okay. So let F from X to Y be linear map and X be finite dimensional. Let me remind you here, it is not necessary Y should be finite dimensional. Y can be infinite dimensional. Okay. So don't get mixed up here. All right. Since X is finite dimensional, the range of F is also finite dimensional. So it doesn't matter what Y is. Okay. That's the point. If X is 0, there is nothing to prove, obviously. If X is not 0, let A1, A2, AM be a basis for X. How do you know a basis exists? Such a finite basis exists if X is finite dimensional. So we assume that the dimension of this X is M. Therefore, it has a basis element A1, A2, AI. Okay. Take any sequence Xn in X. Since A1, A2, AM is a basis, you can write Xn as a combination of A1, A2, AM. Okay. So for a fixed n, there are constants kn1, kn2, knm such that xn equal to kn1 a1 plus kn1 m. So this kn1, kn2, knm is normally called the coordinates of the point xn with respect to the basis a1, a2, am. Okay, standard. So these knj's for n equal to 1, 2, 3, etc., they are all scalars. Okay, they are the coordinates and they are the scalars. If k is real, you get real numbers. If k is complex, you get complex numbers. Okay. If x, so what is that we want to show? We want to show that f is continuous. What does it mean? If you xn converges to x, then we want to show this f of xn also converges to f of x. Okay. Suppose xn converges to x. Okay. And suppose the coordinates of x is k1, k2, km. Okay. Then this k and j also will go to kj as n goes to infinity, but j equal to 1 to m. Yes or no? What I'm saying is the nth component of xn, that is kn1, will converge to the first component of x. Second sequence, the kn2 for n equal to 1, 2, 3, that will also converge. Now, if xn converges to x, why should these sequences k and j also converge? A sequence in Rn converges if and only if the coordinates converges, right? Finite dimensional linear algebra. If xn converges to x, then the corresponding coordinates also converge in the finite dimensional case. Okay, that's a simple thing. So we are using the coordinates k and j will converge to kg. So j equal to 1 to m. So you define x equal to k1 a1 plus k2 am plus kn am. All right. Is this clear? Hello. Is this clear to you?
Yes, sir.
Yes, sir.
Am I audible?
Yes, sir.
So then the rest of the proof is simple. F of xn is f of xn is what? Xn is k1, 1, a1, etc. But f is linear. So this k1, 1 comes out. So you get f of xn equal to kn1, f of alpha 1, etc. an, etc. But this kn1 converges to k1, f of a1 is independent of n. Therefore, when you take n goes to infinity on the both sides, this kn1 will go to k1, fa1 remains the same. And finally, what will happen is you have k of 1 Fk1 plus Km Fn, that is f of x. Why? Because A1, A2, Am is the coordinate, rather K1, K2, Km is the coordinate of the point x. So use linearity here. So this will be f of K1, A1 plus x, etc., plus Km, Am. But K1, A1 plus K2, Am is x. Therefore, the right side will be fx. So limit n going to infinity of f of xn is f of x. That's the definition of continuity in a metric space. So the proof is simple. So by the linearity of f and continuity, scalar multiplication and other things are clear. Okay, so no problems in this problem. It's a simple proof. Now we want to show that if x is not finite dimensional, then there is a linear operator which is not continuous. See, the question is, a base function You know it or not? Huh? Let's be slow when learning, okay?
Sir, for the basis we have for infinite dimension, like infinite basis, when we have like when we write, sir, for finite basis also we have some constants uh, multiplied with the basis values. That constant will only be equal when they are zero, or else they won't be equal. So if we look in that way, then it will be linearly independent, sir.
That way means?
So like the if we have the constants like C1 A1 plus C2 A2 plus C3 A3 and so on, sir, for the infinite dimensional, then it will be linearly independent if C1 C2
But
C3 are not equal and
no, no, no,
only
no,
equal,
no.
then it is equal to
Please
zero.
remember, please remember. You are slightly, you are going off the way, okay? What I am trying to say, you are you are somewhere close to it. It's not the answer actually, okay? You have the set A1, A2, AN is linearly independent. What does it mean?
It means, sir, कि neither each one is not dependent to each other. So, like if we uh, sir, if we have three vectors, so some resultant of two vectors is not parallel to third one vector.
No, no, what I'm saying is for independent set in finite dimension, you have defined properly. Suppose it's not finite dimension, then you are saying that a set A1, A2, AN is linearly independent. What does it mean? I'm talking about the set A1, A2, AN. You are talking of something else.
We are saying
When do you say an infinite set A1, A2, AN is linearly independent? If you don't know, you let me know. Huh? Don't worry.
Sir, it will be a basis for infinite dimension.
Hmm?
Sir, basis for infinite dimension.
No, no, no. You are not getting my point. What is the meaning of AN You are saying it is linearly independent. What does it mean? Because in linear algebra, we have done only dependence and independence only for finite set. Now you have an independent set. What do you mean by it's independent? Quick. जल्दी बोलो. All right. The set A1, A2, An, an infinite set is called linearly independent in a vector space if and only if every finite subset of that is linearly independent. Is it clear?
Yes, sir.
You see, in the linear algebra, you don't define infinite sum. Okay, that is the problem. So, infinite set in a vector space is linearly independent if and only if every finite subset of that is linearly independent. Clear? Okay. Be clear about what is the definition. Otherwise, it creates a mess. So that is what it says. So let X be infinite dimensional. Let A1, A2, A and be infinitely linearly independent. This line you should understand. Now, can any one of these ANs be zero? No. In a linearly independent set, no element can be zero. So you define Xn equal to An over n times norm of An. Because there's a definition here that you are dividing by norm An. If you want to divide by norm An, that norm An should not be zero. Since An is an element of a linearly independent set, it is not zero. So you define Xn equal to An divided by n times norm An. What's the norm of Xn? It will be norm An, that cancels, you get 1 by n. So define this for n equal to 1, 2, 3, n. Then x1, x2, xn is also linearly independent subset. That's obvious. Okay. I mean, you are rescaling, nothing more. And another thing is that norm of xn is 1. 1 by n for each n. All right. So norm of xn is 1 by n. Then there exists a basis of b for which subset of the b such that y is not, since y is not 0, this f of x is b or f of x is b and equal to 0 if x is in that is an obvious if you define something on the basis, etc. This if you have a operator defined on a basis, you can extend it to the whole vector space. Since xn goes to 0 as n goes to infinity, but f of xn is b, which is not 0 for all x in x. Therefore, f is not continuous. Okay. So that is the proof of something which we say that in an infinite dimensional space, you can define a linear operator, which will not be linearly, which will not be continuous. That's the proof. Very important proof. Most of the times in all PhD interviews, in all faculty interviews, this question is asked. Okay. I'll give a simpler proof of this than what is given in this book. Okay. The next one is an important theorem, 6.2. And this is the theorem which we use continuously, in this theorem is let X and Y be non-linear space and F be a linear map from X to Y. You see, this book uses F as a linear map, but most of the books they use T and S. Don't worry about the notation. All right. Then the following are equivalent. F is bounded sphere of radius R, that is U, and take the closure. What is this U0? It is norm of X less than or equal to 1 if X is in U. Then F is continuous at 0. So if F is continuous at 0, then it is equivalent to the first statement. F is continuous on X. That means what? If F is continuous at 0, then the continuity spreads all over. F is uniformly continuous. That means if F is continuous, then F is also uniformly continuous. Finally, norm of Fx is less than or equal to alpha times norm x for all x in x. So this alpha is independent of this x, and alpha is greater than 0, strictly greater than 0. This is the fifth statement. What is the equivalent statement of that? The null space of F is closed and the linear map F tilde from the null space to Y is defined and it is continuous. Anyway, null space is closed is essential. That's what you are going to use. These 6 statements are equivalent. Let me give you some comment on the fifth statement. Fifth statement is that norm of fx is less than or equal to alpha times norm of x. That means if you take a bounded set, what do you mean by bounded set? The diameter of the set is bounded. Okay. So there is an M such that norm of x is less than or equal to M. Such a set is called a bounded set. So if fx is less than or equal to alpha times x, if x is bounded, then alpha times norm is also bounded. That means F will map bounded sets to bounded sets. That is the definition used in most of the books. That F is a linear map is called continuous if it maps bounded sets to bounded sets. Okay. That's the comment which I wanted to make. Shall I write it and show it?
No,
No need, no? Should I write it?
no, sir.
Okay. So let me see where the proof is. This is the proof. So, I mean, he does it in a very funny way anyway, it doesn't matter. So he wants to show, you see, there are 6 statements here. 1, 2, 3, 4, 5, 6. So he's showing that 1 will imply the 4 and etc. 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 Okay. Let us see. So he says, sorry, 1 implies 5. 1 implies 5 means that if f is if maps f is bounded on u0 or, that means this first one is same thing as the fifth one. It's a consequence of the linearity. All right. We show that 1 implies 5. The successive reverse implications are immediate. Okay. That we will see it later. Let norm of fx be less than or equal to beta for all x in u0, u bar 0 r. Why it is true? Because it says that this f is bounded. The first one says f is bounded on u0. What is the meaning of saying bounded? There is a beta for which norm of fx is less than or equal to beta. For all x in this one, if x is 0, obviously fx is 0. There is no problem. There is nothing to talk about. So let's assume that x is not 0. If x is not 0, since the radius of this ball is r, you multiply by rx and divide by norm x, then this element rx over norm x will become norm 1. Okay. So if you take any x which is not 0, this is a standard technique used in this function analysis. You divide by the length of it, then you get a unit vector. So multiply by r, since you are not in the unit sphere, you are in the sphere of radius r, is multiplying by r. To get that, it is in u. So look at rx over norm rx. The norm of this is x over norm x is 1. So it is less than or equal to r. Therefore, it will be in u0 r. If it is in u0 r, it is in the closure also. Now look at f of x. Norm x is constant, r is constant. So it comes out. So you get rx over norm x into norm of, okay, this one, I mean, you take the norm of f of rx over norm x, that's what you have here. Okay. So that will be less than or equal to beta over r into norm x. All right. That's the first theorem, that if norm of fx is bounded by this alpha. alpha, beta over r is the alpha that you have. Okay. All right. Now we show that f is continuous if and only if 4 holds. So what is 4? One is f is continuous, 2, and 4 is that it is uniformly continuous. Okay, let us see it. Let f be continuous on x. Then the null space of f is f inverse of 0. It's closed in x. Since 0 set is closed in y, so therefore this function is closed. Okay. So that's the first one. Now x over zf is a non-linear space with a quotient norm. Then it can be seen that this also is simple proof. Okay. I'll omit it for a while. Now, the successive reverse implications are immediate. What is the meaning of that? Reverse implication is 4 implies 3, 3 implies 2, 2 implies 1, like that. If f is uniformly continuous, that's 4, that will imply 3. Obviously, uniform continuity will give you continuity. That's obvious. So 4 implies 3 is obvious. 3 implies 2 is obvious. F is continuous everywhere. Since f is continuous everywhere, it's continuous at 0. So that is also true. Now, f is continuous at 0 will also imply that f is bounded. No issues, right? Implications are proved here. Okay. So that is the story. I'll send you alternative proofs for this, because not very happy with this sort of proof when I am there in Mizoram. Okay. So
Okay, sir.
I have sent these notes to you. I hope you have got it.
Yes, sir. Yes, sir. We all got it.
Now, do you have any comments to make? It's 12:48. They told me that it's a class. It's only for 50 minutes. Okay. Today I'm little late, but I have to go out somewhere. So I would like to stop the class now. Do you have any quick comments, questions to make? Today I am
No.
very slow because continuity of a linear operator is very, very important. Kindly read it up. Okay.
Okay,
Then
sir.
we'll discuss it again. Okay.
Okay, sir.
Bye. Have a good day.
Bye. Thank you, sir.
Happy Ganesh
Thank
Chaturthi.
you, sir.
Happy Ganesh Chaturthi, sir.